We'll continue the discussion about optimal climate policy by looking more closely at the role of time discounting, starting with the Ramsey rule. Climate change is a long-term problem, climate change is an uncertain problem, climate change is a global problem. These three statements are indisputable. The implication is that if you do not care about the distant future, if you do not care about remote probabilities, if you do not care about faraway lands, you do not care about climate change. And I will make this statement more precise, starting with talking about the distant future. We've seen this table before. These are estimates of the social cost of carbon. And what you see is that if you use a high pure rate of time preference, say 3%, you want to impose a carbon tax of $43 per ton of carbon. But if you use a low pure rate of time preference, then you want to impose a much higher carbon tax, say $686 per ton of carbon. So what is this pure rate of time preference? It's a key parameter in the Ramsey rule. So let's define the net present value of receiving $1 in t years time is e to the power minus rho t, and let's call this epsilon. Now this may not be the discount rate that, or the discount factor that you are used to looking at. You may be much more familiar with this expression here, 1 over 1 plus r to the power t, or 1 plus r to the power minus t. This is what we typically use when we calculate the net present value of something, but the t here essentially then goes in discrete steps. And usually the way we think about interest rates is that you pay an annual interest rate. But why would you pick a year as your time step? You can do it in months or you could do it in days. Actually, your bank charges you interest at a daily rate, not at a yearly rate. But why pick a day? You can do it for an hour, you can do it for a minute, you can do it for a second. Now, if you let the time step shrink in this equation here or in this equation here, if you let the time step shrink to 0, this expression converges to this expression. Why do I want to work in continuous time with infinitesimally small time steps? Actually, the math is easier in continuous time than in discrete time. So that is our definition of the net present value of $1 in t years time. And here we have it again. Now, discounting is essentially an indifference equation. Essentially what you say, well, I want to make this investment if my return, which is in the future, is at least as valuable as the investment today, right? So that is what you want to do. So you want to equate the utility of receiving $1 in the future to having epsilon dollars today. And so how does this work? The value of epsilon dollars today is that epsilon times the marginal utility. This is du dc at time 0. So this is your utility gain of epsilon dollars today. This is the utility gain from $1 in t years time. So here we have the $1. We multiply it with the marginal utility, the UDC or U sub c at time t. So this is your marginal gain in utility of $1 then. And that we multiply with the value of future utility, and we denote that as e to the power minus rho t, where rho is your pure rate of time preference. This is essentially your discount rate of utility. Now, this expression can be rewritten by bringing u sub c to the other side of the equation. Now, if we assume a CRRA utility function, then the UDC or u sub c is c to the power minus eta, where eta is the curvature of the utility function. It's still not there because we have a CT and a C0, but CT is essentially relative to today's consumption, is essentially the growth rate, is essentially today's consumption times the growth rate of consumption. So we can write CT as C0 times e to the power GT, that's the growth rate of consumption. G is the average growth rate, and T is the period, the length of the time that has passed. But then we have to raise that to the power minus eta G, and that is where the minus eta pops up. Now, good thing is that we now have C0 to the power minus eta T on both sides, so that cancels. And what we have is that the expression that remains is e to the power minus rho t minus eta gt. That by definition is equal to our money discount factor, e to the power minus rt. We take the log on both sides of the equation and we drop the minus signs, and we have the Ramsey rule that says that the money discount rate is equal to the utility discount rate, or the pure rate of time preference, plus the growth rate of consumption times the curvature of the utility function. Now, how does the eta G work? Why does this pop up, and what is the intuition behind this? Let's look at the utility function. We have consumption on the horizontal axis, we have utility or happiness on the vertical axis, and then the red curve is your utility function. Now, what is saving? Saving means essentially that you do not consume your money today, but you save it for later, and you increase your consumption tomorrow. So you reduce your consumption today in order to increase your consumption later. Now, what is the trade-off that you make in utility terms? Well, if you reduce your consumption today, you lose utility. That is a loss. In return, you gain consumption tomorrow, and as a result, your consumption, your utility tomorrow increases. Now, in the graph that you're looking at now, the horizontal distances are equal. So the assumption here is that there's no interest. And if you further assume that you expect to be richer in the future, then this is a bad deal, right? Because if you expect to be richer in the future, then the utility loss from saving today is smaller than the utility gain from increasing your consumption tomorrow. So really, in order for us to be indifferent between the two, what we need is that the vertical distances are equal, that your utility gain tomorrow is equal to your utility loss, exactly compensates your utility loss today. And that implies that the horizontal distance is much larger, and that is your eta G. Your eta measures the curvature of the utility function. And if this utility function were linear, then horizontal, then equating the vertical distances would lead to equal horizontal distances by definition of linearity. So that is why your eta is important. Your G is important. Your G is important because it measures how fast you are moving to the right, how fast you are growing richer. So this is the Ramsey rule, named after Frank Ramsey, one of the most brilliant economists to have ever lived. And essentially the Ramsey rule says that we discount future monetary returns are, for two reasons, rho and eta G. Or in words, we discount the future because we will be richer and happier then, or at least we expect to be richer and happier then. And again, savings is essentially a transfer of money from today's self to tomorrow's self. And if you expect that you will be much richer in the future than you are now, then why would you put £100 aside today in order to be £100 richer tomorrow? If currently you are on a student income and next year you are working, why would you transfer money from your poor today selves to a much richer future self? Right? So that is one reason to discount the future. And this is largely uncontroversial. The other reason to discount the future is that we are impatient. We want the good stuff and we want it now. Now, that is extremely controversial. I'll come back to that. I think that the ATG part should also be much more controversial than it is typically assumed to be, for two reasons. One, it's actually very hard to measure and define your eta. Second, what enters into this calculus that I just showed is the growth rate of the things we care about. But in all applications that are out there, the G that is used is the growth rate of material consumption, of things that we can easily measure. Now, before I turn to the controversy about the rho parameter, the impatience or the pure rate of time preference, it is important to note that derivation of the Ramsey rule that I have just given is all from a consumption perspective. There's, of course, an alternative interpretation of the interest rate, and that is the opportunity cost of capital. Now, in the same paper that he derived this particular rule, Ramsey also showed that in a dynamic equilibrium, the opportunity cost of capital and consumption rate of discount are equal to each other. So it's just two sides of the same coin. I find the consumption discount rate much more intuitive to explain and understand. Now, the choice of the pure rate of time preference is of crucial importance for long-term problems such as climate change. So what should the value of rho be? What should our pure rate of time preference be? Well, there is no easy solution to this. If you're a Democrat, then you would say, well, the discount rate that we use for public policy, for public investments, should reflect the will of the people. If you ask people what should the discount rate be, if you ask them to express their time preference, then you will find that everybody discounts the future, not just because they expect to be richer and happier, but they are impatient. So if you ask people, when should the new Billie Eilish album come out, they will tell you tomorrow, not next year. Or if you ask them when should J.R.R. Martin publish the next installment of the Game of Thrones, they say, I want to read that book tomorrow. I don't want to wait another 10 years. George, please hurry up. So if you ask people about things that make them happy, that have no material connotations, they will still say, I want the good stuff, I want it now. If you ask a child, do you want an ice cream today or tomorrow, they will tell you, I want the ice cream today. We discount the future, we discount future happiness. At the same time, every philosopher and every religious authority since at least Aristotle have taught us and argued that discounting the future just because it is the future is wrong. It's immoral. And this is particularly pronounced if we are talking about intergenerational problems, because essentially if you're discounting the future just because it is the future, then what you say is that people who are born, or people who will be born in the year 2040, are less important than the people who were born in the year 2000. That is one of the implications of using a positive pure rate of time preference. You say that certain people are less worthy than others just because they were born later. So this is an immediate conundrum. Now, another principle that you want discounting to follow is that you should not ignore the far future. You should not say, well, people discount the future for all sorts of reasons when you're talking about books or albums or investments that they make in the stock market. They show that they discount the future and discount the future sometimes very hard. And because of that, we should also discount problems such as climate change and basically ignore it because most of it is in the far future. That is wrong. That is intuitively wrong, that we should ignore the long-term consequences of our actions. So some jokers have suggested that one solution to this is to use different discount rates for different problems. That if we are confronted with a problem like climatic change, we should use a low discount rate. But if we are confronted with an ordinary problem, like how much money should we spend on our education or how much money should we invest in our pensions, then we should use a much higher discount rate. We should be much closer to the observed will of the people. Now, that is not a solution either, because the third principle that discount rates should follow is that they should be consistently applied across public policy. And you could, for instance, think about investing money in greenhouse gas emission reduction, and you can do a prediction there and say, well, because of the investments we make in the year 2020, we're going to save one life because of reduced climate change in the year 2040. And that is important, and it's important to improve human health and reduce risks of premature mortality. There could be an alternative investment that you spend the money on road safety, for instance, and because you spend money on road safety in the year 2020, you're going to save one life in the year 2040. That life that you save in the year 2040 should be valued the same regardless of whether you save that life through greenhouse gas emission reduction or by building, say, roundabouts or putting traffic lights up. You should be indifferent between the two. A life is a life, 2040 is 2040. So you cannot just say, we're going to use a low discount rate for long-term problems and a high discount rate for short-term problems. That just doesn't compute. Then it leads to inefficient and, in fact, immoral application of money. The problem is that if you want to meet all these three criteria, you want to reflect the will of the people, you want to take proper regard to the far future, and you want to be consistent across public policy, that you cannot solve this with exponential discounting, the type of discounting that I've shown you so far.